Hello everyone, I welcome you all once again to my channel, and this specific presentation I am making with the narration because this particular topic, as you can see on the screen, nucleophilic addition reactions of carbonyl compounds for class 12th. This topic generally confuses many students. So, to help you all, I am discussing the nucleophilic addition reactions of carbonyl compounds from the chapter Aldehydes, Ketones and Carboxylic Acids, class 12th chemistry. Let's get started. So, this is the first chemical reaction of aldehydes and ketones in the chapter. The reaction is quite simple if you understand the basics. This is carbonyl compound. As you can see here, we represent it like carbon making a double bond with oxygen, and this is a polar bond. That's why we write delta positive and delta negative here. Now, in the nucleophilic addition reaction, the nucleophile, we generally write Nu with a negative charge because nucleophile is electron rich species, right? So, it is coming and attacking at carbon. Why? Because carbon has the positive charge here, and in the process this double bond will convert to a single bond when nucleophile is attacking on the carbon. So, electron density from here shifts towards oxygen and you get this intermediate. You should notice that it was planar because the carbon here is sp2 hybridized and here it has become sp3 hybridized. So, it becomes tetrahedral, a very important change in the geometry after the attack of the nucleophile. These small basic things you should keep in mind. As I always tell my students that from NCERT, from any line they can make a question for you. So, the concepts are not tough, but you have to be very careful when you read NCERT. Okay. So, we have understood till here. This was the intermediate. Now, when the nucleophile has attacked and this electron density has shifted, you should show a negative charge here. And then if there is a negative already, H plus will come immediately. That's why this is the fast step, two opposite charges attracting each other, and you finally get the addition product. Let us understand this with specific examples. But first of all, we have to pay attention to this reasoning question which is generally asked, very important reasoning question, that why aldehydes are generally more reactive than ketones in the nucleophilic addition reactions. Now, what happens here, that you have a carbonyl compound and the carbonyl compound has this carbon with delta positive charge, where nucleophile, which is in search of the positive charge, will come and attack. Now, what happens if it is an aldehyde? There is only one R group and the other one is hydrogen. So, the R group, which is electron donating group, does not reduce the positive nature of this carbon where the nucleophile is attacking much. But in case of ketone, there are two R groups here, both electron donating R groups. So, the positive charge, the ability of this carbon to attract the nucleophile decreases because these two R groups are shifting the electron density towards the carbon. That's the reason that aldehydes are more reactive than ketones in nucleophilic addition reactions. This was the electronic reason that I just explained. The other reason is steric factor. You can understand this very well, that if there is carbon on which the nucleophile has to attack, it has a double bond here, and the two attachments, if these two attachments are hydrogens formaldehyde suppose, or one of them is hydrogen and the other is R group, still it is easy for the nucleophile to come and attack. But if both are R groups, obviously R groups occupy more space as compared to hydrogen. So, it will be difficult Not impossible, but difficult for this nucleophile to attack on this carbon because of the steric factor. That these two R, the smallest R group is CH3. That also occupies a lot of space as compared to hydrogen, and if there are bigger R groups, then all the more steric factor, right? That's the reason. So, there are two reasons, steric hindrance and electronic reason. Then this question is also generally asked that if you compare benzaldehyde with propanol, which is more or less reactive in nucleophilic addition reactions and why? So, in case of propanol and benzaldehyde, propanol is CH3, CH2, CHO, and benzaldehyde I am comparing it with benzene with a CHO. Now, if you draw the resonating structures of benzaldehyde, you will never find positive charge on this carbon. The positive charge, because it is electron withdrawing group, the positive charge will always reside on the carbons of benzene, not on this carbon, and nucleophile comes and attacks this carbon. So, due to resonance, what happens? You will find the positive charge here. You will find the positive charge on alternate carbons in benzene when you draw the resonating structures, but you will never find it on this carbon, which is carbon belonging to carbonyl group. That is why the polarity of the carbonyl group is reduced in benzaldehyde due to resonance. Why am I underlining this? Because this is the most important sentence. This should be there in your answer, and then we consider this the complete answer. So, instead of writing a full paragraph without keywords or important sentence, just one or two, your answer will not be considered complete. So, you have to practice to write to the point, specific answers, apt answers. That is why all this information is very important to understand. So, if they are asking you such a question, they may ask you this for 1 mark or maximum 2 marks. Then you have to answer it like this, as I am explaining, that the carbonyl group of benzaldehyde is less electrophilic. That means this carbon is not able to attract the nucleophile as compared to the carbon of carbonyl group of propanol, because the polarity of the carbonyl group is reduced in benzaldehyde and the positive charges are on the carbons of benzene instead of this carbon. So, it becomes less reactive, right. Let us understand the specific examples now, very important examples, and you will notice that here nucleophilic addition will take place and it will be followed by elimination also in some cases. So, the first addition which is explained in NCERT is addition of hydrogen cyanide. If you take hydrogen cyanide, it dissociates to give you this nucleophile cyanide and H plus is separated, right, temporarily. So, when the cyanide is attacking on the carbon, simultaneously this shifts, that I explained in the initial slides. From the sp2 hybridized planar 1, it becomes tetrahedral intermediate, which is here. And then finally, this is the fast step, H plus will come. This was the slow step when nucleophile was attacking. As compared to this, this is the fast step where H plus is attacking, because negative is already there. So, H plus, which was removed from here in the beginning temporarily, I said, that will come and attack. So, you get this compound, this is called cyanohydrin. When you have cyanide and OH on the same carbon, we call it cyanohydrin. One example. The next example, very important, is addition of sodium hydrogen sulfide. In this, we expect that the bond is going to break like this, Na plus and HSO3 minus. So, here is the nucleophile. Same way the nucleophile is attacking here, this will shift here, you are going to get this intermediate. Simple. Now, this intermediate is in equilibrium with another crystalline form. See the difference carefully. What is the difference here? The difference is that you have H here, Na here, and here the Na and H, they have exchanged their places and it has become crystalline bisulfite addition compound. For aldehydes, the equilibrium shifts towards right more, and for ketones it shifts towards left more because of the steric reason. Because of steric hindrance, if there are two R groups here in ketone, it's not going to be very stable. That's why it shifts towards the left. And this is a very important reaction for purification of aldehydes, because generally aldehydes are more reactive for this reaction. So, if you have a mixture, right, you have impurities and aldehydes, and you want to separate aldehyde from there, you will simply add NaHSO3. NaHSO3 will undergo reaction with the carbonyl group, aldehyde there, RCHO, generally I am writing, and it will give you the product which shifts towards this and gives you the crystalline compound. This crystalline compound is water soluble. So, you will separate it, and after separation you will take dilute acid or dilute alkali and it will give you the aldehyde back. So, this is how we use it for purification of aldehydes also, a very important reaction. This reaction we have already done in the previous chapter. There we explained this under the formation, the preparation part of alcohols. Now, in this reaction you have, suppose, an aldehyde which is HCHO. When you have HCHO, the first member of the aldehydic series, methanol, formaldehyde, and you reacted with Grignard reagent. Grignard reagent dissociates like this. You have plus and you have minus here. So, this is the nucleophile, and you can see the nucleophile is attacking the carbon, it is simultaneously shifting here. When this is happening, then you get this adduct, you get this intermediate, right. What happens if you just see this exactly like the earlier ones we understood? You have a carbonyl group, this was the carbonyl group, and here the Grignard reagent was used, negative, it is attacking here, it is shifting here. So, it is producing O minus and R has attacked here, and you have this MgX plus, so MgX will come here. So, you have this tetrahedral part as you can see here. Now, you hydrolyze it, you take H plus and water, and the bond breaks from here, OH from water comes here and H comes here, you get the alcohol. If it is first member of the aldehydic series, you can see you are getting a primary alcohol. If I start the reaction with any other aldehyde, I will get a secondary alcohol, and if I start the same reaction with a ketone, I get a tertiary alcohol, as simple as that. So, this is also coming under nucleophilic addition reactions. Next is addition of alcohol. If you take an alcohol, then it dissociates as alkoxide ion and H plus ion. This RO minus, alkoxide ion, is the nucleophile. So, this is going to attack on the carbon of carbonyl group. This will shift like this, you are going to get this intermediate. This is called hemiacetal. What is a hemiacetal? When you have alkoxide OR group and you have OH group on the same carbon, you call it hemiacetal. Then you are taking one more molecule of alcohol, same way it will dissociate, another nucleophile is coming and attacking on this carbon, simultaneously this OH will go out and you get water. H plus from here, OH from here will give you water, and OR minus, another OR minus has attacked. So, now I have two OR, two alkoxide groups on the same carbon. This is called acetal. This is a very important reaction under this. We start with ethylene glycol and we are taking a ketone here. So, same way it will dissociate, you get this big nucleophile, H plus is separated. This is making a bond through oxygen, simultaneously it shifts here. So, you will be getting an intermediate, and in the intermediate the CH2OH and CH2O. This big group is attached to carbon. I will show you here. We will take a ketone, C double bond O, and we are taking ethylene glycol, CH2OH and CH2OH. I am saying the bond breaks from here. So, it attacks here, it shifts here. So, we will be getting RCR. This is as it is. This has converted to O with a negative charge, and through the oxygen, this nucleophilic part has attacked here, and you know that here hydrogen will come finally. Same way, when the bond breaks from here, this negative part is attacking here and simultaneously this is going out. When this happens, you are getting the product as you can see here. This is called ethylene glycol, because this is ethylene glycol. This is called ethylene glycol ketal. Here from aldehyde it was acetal, from ketone we get ketal. This particular product, you have understood how the reaction is taking place. So, you can predict it. Remove oxygen from here, remove 2 hydrogens from here to give water, and show the cyclic product as it has been shown here. That will be easy for you to remember. I will write here and tell you once again how to remember this, because you have understood how it is happening. So, for MCQs and all, you can give the answer quickly like this. I said remove water, and then whatever is left, show the cyclic product. Carbon should make 4 bonds, then you have this CH2, CH2, this. This is the ethylene glycol ketal. Simple. Now, the last example, which is a big one, it has many parts, but it is not tough at all. Under nucleophilic addition only, ammonia and its derivatives. Ammonia is NH3, and here how they are writing it, NH2 and H. This is NH3. I will show you a table and explain it to you, but before that you have to understand that ammonia is this, and derivatives, if I put alkyl group in place of Z, it becomes RNH2. If I put aryl group, it becomes C6H5NH2. If I put OH in place of Z, it becomes NH2OH. So, you have a full table for that. We will come back here to understand, but before that you have to see that how this is coming under nucleophilic addition reactions. It happens the same way. You have nitrogen with a lone pair nucleophilic part. So, what will happen? This is going to attack on carbon. It will be offering the electrons for making bond here. Simultaneously this shifts here, and when nitrogen is making a bond with carbon here, then one of the hydrogens comes out. So, what is left? NHZ. You can see NHZ here, where Z can be any one of them, maybe hydrogen also if it is ammonia, and this O minus will get the one hydrogen which was removed from here, and it shows you the OH. And finally, it loses water. As I told you in the beginning that these are, some of them are addition elimination reaction. So, this comes under elimination, OH and hydrogen. Water is lost, and finally, you get this product after elimination. Now, quickly, if you have to predict the product, you can show removal of H2O and the remaining part will give you the product. This is an easy way to understand, but it does not mean that ammonia and its derivative, they are acidic in nature. They are not acidic at all. The reaction is taking place because nitrogen has lone pairs, it can offer electrons acting as the nucleophilic part here and attacking the carbon of carbonyl group, and finally when you get such an intermediate, here the elimination is taking place, it is losing water. To remember it so that you don't write the products wrong, you can remove water for yourself like this, but don't get confused with the mechanism. This is a simple addition, nucleophilic addition and elimination reaction. Okay. Now, let us see how we can predict the products quickly. This is the table. Now in the table, everywhere I can write NH2 for myself. NH2H, this is ammonia. NH2R, this is amine. NH2OH, this is hydroxylamine. NH2 is hydrazine. I am writing, Z part is given, I am writing the remaining NH2. And if I put NH2 here, it becomes phenyl hydrazine. If I put NH2 here, it becomes 1, 2, 3, 4. 2,4-dinitrophenylhydrazine. This is also written as 2,4-DNP, the reagent. And if I put NH2 here, it becomes semicarbazide. So first two columns are giving you the ammonia derivatives and ammonia itself and the name of the reagent, right. Now you have to predict the product. So you simply have to write, as I told you, C double bond O here. When you write C double bond O here and you remove this water, what will you get? C double bond NH. This is the product and this is called imine, right. Same way, write C double bond O here, the carbonyl group. Remove this for yourself. This is the easy way to remember the products, because everywhere, even if they are not asking, you are not supposed to show the attack of lone pair of nitrogen on carbon and then show the intermediate and then remove water. This is the quick way of remembering the product. So what is left? C double bond NR. This is substituted amine, which is also called Schiff's base. Then you have this hydroxylamine, C double bond O, remove this, you get C double bond NOH. This is called oxime, you have to remember the names. So first three you have understood. Same way, C double bond O, remove water, you get C double bond NH2. This is hydrazine, this was hydrazine, so product, this is hydrazone. Instead of I, you write O here in the product. Remember it like that. If this is phenylhydrazine, the product has to be phenylhydrazone. And remove water, the structure of the product is here in front of you. C double bond N, NH and then benzene ring attached to it. I hope the first 5 are clear, easy to remember. Let us see the last 2. The last 2 here, same way, you will put NH2 here for yourself, carbonyl group here, same way NH2 here and carbonyl group here. Remove H2O. You will be, this was 2,4-DNP, 2,4-dinitrophenylhydrazine, 2,4-DNP, and the product would be C with 2 bonds already, double bond and then N, N, NH, NH, benzene with nitro groups at 2 at 4 positions. 2,4-dinitrophenylhydrazone. Same way here, carbon, this is semicarbazide. So this is C double bond N, this N, NH, NH, CO, NH2, semicarbazone. Semicarbazide से क्या बना? Semicarbazone. 2,4-DNP, 2,4-dinitrophenylhydrazine is the reagent और मिला क्या? 2,4-dinitrophenylhydrazone. This is how you can remember this table, very important table. Competitive exam में भी पूछते हैं, board में भी. So this is very important. This is how you predict the products. And there is a very important reasoning question related to the semicarbazide. You will notice that there are 2 NH2 groups, right? But the NH2 group which is attached to CO, this one, this does not take part in making the product with carbonyl group. It is this NH2 which is besides NH, it is reacting with carbonyl. The reason is that this particular nitrogen here, this is involved in resonance with carbonyl group because it is directly attached to C double bond O. The other NH2 group is not attached to C double bond O. So here the lone pair is available. This can act as a nucleophile and show the reaction with the carbonyl group. It can attack here. This is the reason. And this question is asked in the exercise also, that in semi-carbazide there are two NH2 groups but only one takes part in nucleophilic addition. So this is the reason that the NH2 group which is attached to CO is involved in resonance with carbonyl group. So it does not act as a nucleophile for reacting with carbonyl compounds. So this is the end of this presentation. All the nucleophilic addition reactions are very easy to understand. I hope the presentation will help you. I'll keep coming with small presentations like this. I hope they will be making the chemistry easy for you. Thank you so much.